All right. Now starting the last part of the course. So I am making a few changes for exam 4. So let me just write those down just so you guys have them. Exam 4 is now going to be torsion only, which, as you guessed it, the topic for this week and moving forward is going to be torsion. All right, so beam deflection has been removed. Column buckling, I'm thinking of just removing entirely as well. And this I'm basically adopting from Professor Simon because he does an entire exam on torsion in itself. So I just figure instead of just rushing through everything, I figure I'll treat it similar to how we did the normal stresses at the beginning of the semester, because with torsion and torque, you guys can have statically indeterminate members, composite members also. So I'd rather just not rush through everything. I'd rather do those problems with you. And plus he said that some of the algebra associated with it can be a little bit confusing when you're doing the calculations, because it's not as simple as just like taking areas anymore. So Olivia, you had your hand raised? Yeah, and he drops the lowest one also. So.
Oh, okay. So he does entire unit on torsion?
Yeah, basically everything that we've covered is exactly the same as what Professor Simon had. The only thing that I would say is slightly different is the fact that Professor Simon doesn't do stress transformations. And he'll usually do beam deflections, which, because I figure beams was already all of last exam, I'm just going to ignore it because there's really no point in showing you guys beam deflections after we've covered beams. So I'd rather just keep everything all interrelated with each other. Does that make sense? Yeah. But if you guys are interested, I'd be willing to show you guys how it's done. Yeah. All right. So for torsion, a lot of the equations are nearly identical to how you had it for stresses and strains at the beginning of the semester. All right, so there are a few differences. Now, let me ask first, does everyone know what torsion is? Not really. All right, so torsion or torque is, well, torsion is a type of shear stress that's associated with twisting. All right. So, for example, if you have like a overhang on like a building, let's say that this is like a beam, and then this is like a overhang for a concrete building, right? And let's say that this is all monolithically cast, right? What's going to happen? Well, you might have some snow loads accumulating over here, right? And so what's going to happen is that part of the beam, this part, is going to undergo some type of bending, right? But what's going to happen to this beam right here? Is it going to bend? Well, it will, right, if you look at it from another perspective, but it's also going to twist, right? So this twisting is going to kind of look somewhat like this. Right? It's going to twist. Maybe it's not going to be nearly as pronounced as this, but you guys get the picture. Now, when it comes to something like this, whenever we're calculating stresses, I'm only going to really give you guys circular sections But if I ask you guys for like a torque, for example, it's fair game because it's basically just another type of moment. So, yeah. So torsion is just a shear stress that's caused from twisting. What causes this twisting? The twisting is caused by a torque. Now, who here has heard of torque before? You have. What do you think of when you hear the word torque?
Like power.
Mm-hmm. Exactly. It's like horsepower in an engine. It's officially for like the mechanisms of the gear and like how fast they rotate and how much resistance that they have. It's how the engine basically runs. It produces power. You know, I'm not going to go too much into the power. You know, if you guys have the textbook, it actually tells you how to calculate horsepower with respect to certain values of torque. So it's very interesting if you like doing like machine work or whatever. But this torque is basically just a type of moment that acts in the cross section. Now, what we need to recall is several different terms. So let's recall 3 different terms: tau, gamma, and g. What was tau? What did we call tau throughout the semester?
Like the formula or like
What it is.
shear strength?
Shear stress. Reason being is because there are separate equations for torque and torsion, which are just entirely different than the equations that we'll see. Some of them are very similar in derivation and how they look, but generally speaking, some of the properties for them are different. What about gamma? What did we say that was?
Not shear strain.
It is. It's shear strain. And then lastly, what did we call G?
Modulus of rigidity.
Yeah, modulus of rigidity. Which another way of calling it is shear modulus. All right. Now, when we apply this torque, is the deformation going to elongate? Is it going to compress? Is it going to twist? Is it going to bend? How's it going to look? Let's say you take your pen and you twist both ends. All right. How's the cross section going to look? Here, I'll do this. We apply some torque at the end. We call torque by the letter T. And then if we were to look at this in like a cross-sectional view, this could be just some arbitrary shape. I'm going to use a circle because most of the problems I'm going to give you for calculating shear stresses and shear strains and deformations are going to be circular in cross-section. Very few instances where I'll give you a non-circular cross-section. All right. This circular cross-section has some radius, r. And so if we look at this point here, let's call this A, point A. Or no, 0.1, just so that way I can kind of distinguish between A and 1. If you were to twist this, how's it going to look? Where's that 0.1 going to go?
The opposite side.
What?
Be the opposite side.
Well, it's just going to rotate some degree, right? It could be like way down here. It could be up here, right? So let's say that it rotates up here. And we'll call this point 2. And from this deformation, we call this deformation phi. That's its rotation that it undergoes. So in a very similar way to how we calculated axial stress and deformation, we have an associated deformation with that as well. So phi is the angle of twist, which is the deformation. All right. Now, we could do a bunch of algebra and small angle approximations, and we basically find from this geometry that the tangent of the angle gamma is equal to the radius times phi over the length of the shaft, this being the length. And then because it's small, it's approximately equal to the shear strain. Now, are there any questions about this at all? This looks very similar to like the shear strain equation when we were dealing with planar shear strain, right? If you guys look back at your notes for that, you guys would see where the equation kind of comes from, and you would get a very similar thing here. All right? Now, if we use Hooke's law and focus primarily on this part here, does anyone remember what Hooke's law is? Think back to a first weeks of class. Anyone? I'll give you guys a hint. It's what the shear modulus is equal to. What you need to do is look way back at the beginning when we were drawing those diagrams initially. Got it?
This is a tau over gamma.
Yeah. It's tau over gamma. So shear stress over shear strain. So applying this, what we end up getting now, when we plug in that gamma equation, is that we can calculate the shear stress in terms of the shear modulus times the radius times the angle of twist divided by the length. So with all of this in mind, we can then kind of calculate what the shear strain is. So not shear strain, the angle of twist. And this angle of twist is going to equal the stress times the strain divided by shear modulus divided by radius. Now that's great and all, but the question still begs, how do we get the shear stress? Because I still haven't shown you guys that yet. This is all just associated with the deformation. And I should note that the angle of twist is going to be in radians, which means if you want it in degrees, you have to multiply it by 180 divided by pi to get it in degrees. Does that make sense? Because if you went to a contractor and you were like, I need this to not be able to deform more than 0.00813 radians, they're going to smack you over the head with it. All right? But now we need to ask, how do we get it in terms of applied torque? Well, there's a lot of calculus that kind of goes into this, all right? I'm not going to go too much into it, but it involves looking at the cross-sectional area at a microscopic level, looking at how it kind of formulates. But the torque can generally be defined as either an applied force, it's either going to be given to you, usually, or it's going to be equal to some force times its perpendicular distance. Because again, the torque is just some kind of moment, right? So from here, we can kind of rewrite this whole thing knowing this. And what we'll end up with is that the angle of twist is just going to equal the torque times the length divided by the shear modulus divided by this new property known as J. Now J is what we call the polar moment of inertia. This J is a cross-sectional property within your tables. So if you guys pull out your appendices, there are different values of J. It's going to be specifically Appendix B. Which for circles, which is what we're going to mostly be dealing with in this class, is going to equal J is equal to 1/2 pi r to the 4th. Which another way that this is really derived is just from J is equal to Ix plus Iy. Now, are there any questions at all about any of the equations that I have given you? So in general, the main equations that we really need to know, which if you guys want, I'll actually give you guys flashcards right now. So that way we can just write down all of the equations, all down. Here you go. And you guys, I don't think you'll need both sides for the last exam, but I'll let you guys do both sides since I think most of you were some of you may be stressed. especially with all of the final exams coming up. Who's feeling ready for the end of the semester? You are? Oh, that's good. All right. So, the main equations that we really need to know, I'm actually going to write them on the board here, just because they're already in the lectures. And I don't want to keep rewriting the same thing like 4 times, 5 times. So, we are going to have torque, which is equal to some force times a perpendicular distance. Oh, that's supposed to be R. All right, sometimes the torque will just be given to you in terms of a twisting force. Sometimes you're going to need to calculate. The shear stress is going to equal, I don't remember all of the equations just off the top of my head. Oh, I forgot to add one more thing. From all of this, we can basically rewrite this, the shear stress then, where now the shear stress, tau, is just going to equal the torque times the perpendicular distance divided by J. And we can do that now because we have this definition here. So, the main important equations we need to recall. L over GJ, right? Yes. Gamma is equal to the shear strain which is going to equal shear stress over G. And then what's lastly J, which is equal polar moment of inertia. All right, so those are primarily some of the main equations that we really need to deal with. That's all I'm really going to be covering mostly today. And then next class we'll go into more complicated topics such as composites probably. Yes?
So for the angle of twist that you have on the board here,
Yeah.
why are we using the shear stress? Because on here you have it just with the regular T. Torque. Would that be torque? But then on here you have it with the shear stress.
You could use either equation. So the thing is, like, the two equations are somewhat different depending on what you're calculating exactly, what terms you're using, but both are correct. So if you computed the shear stress, you could use tau gamma over G R. So you could use either or. Generally speaking, more likely than not, you're almost going to always use this.
Okay.
The reason being is because you're always generally going to know the torque,
Okay.
and it's just a plug and shove problem at that point. Whereas
Okay.
with this, it requires you to calculate everything else.
Okay. Thank you.
Are there any other questions? Yes.
What about the one like all the way at the top? The gamma on the bottom and the J, those are interchangeable?
GR fee over. No. You're right. Thank you for correcting this. This should be. Is it gamma? Let me double check. Yeah, wait, why did I write that? Man, all my shit is messed up. Should be GR fee. I don't know why I put it wrong. Wait a minute. That's the correct term, so let me correct that. Sorry. I think I'm like, these notes are like all messed up. This was a typo. So this should be L, which would make much more sense as to how I got certain terms. That in turn changes this to L, which is how the L is on the numerator. I was wondering where I went wrong with that. So this should be L also. That is a very good catch. GR phi over L. Yes. And then G phi J over L. Yeah, that's too important. Okay. That should be all the equations now. And then, of course, you could derive more equations accordingly by just manipulating everything. All right? Any questions? If not, I'd just like to immediately jump straight into a really quick problem. Let's say we have, let me write an example. We have a rod here. Yes. And let's say that it's subjected to some force of 5 kips. All right. But if we look at it from like a side view here, right, then how does it look? It's going to look something like this. It's going to be like circular in cross section, but that 5 kip force is like loaded on a plate here, right here. Call this section A. And let's say that from this location here, from the center line, it is located 6 inches. Simply put, what I want to know is, what is the torque? Olivia, you got it? No? Who here's got it? Michael, you got it?
You just multiply the -5 kips times the 6 inches.
Yeah. So the torque is just going to simply be T is equal to 5 kips times the 6 inches, which is going to give you 30 kip inches of torque. 6 inches is the radius because it's the perpendicular distance with respect to where the center of the rod is. So there's going to be a twisting of about 30 kip inches. Does the sign matter? Yes, it does, especially if you start looking at more and more. Like if I threw like 4 or 5, then this, if we look at it about how it rotates about its centroid here, how's it going to be? Clockwise or counterclockwise? You said it initially.
So it would be negative.
Yeah, it's clockwise. It's clockwise, so it's negative. So CW means clockwise, or you could just write -30 kip inches. Simple as that. Now, let's say that of the 6 inches, the rod, this radius here was about, I don't know, 2 inches. What I want to know, what is the shear stress now? All right. What is the shear stress in the circular rod, I should add? I'll give you guys a few minutes. Anyone got it? Yeah.
I got -7.62.
How'd you calculate it?
I did a TR over J.
All right. How did you calculate J?
Would it be 1/2 of IR?
What did you use for R?
For what? For R?
What'd you use for R?
Would it be 6 inches?
Nope. It's 2 inches. So here's the thing. When you're calculating a torque, another way of thinking of this is this now, equivalent system, basically becomes this. You have the rod here, this is 2 inches, and then this torque becomes 30 kip inches. This entire flat plate here is not even subjected to any type of twisting whatsoever. That would be subjected to bending, which we're not dealing with. If you guys wanted to determine what the thickness of that plate would be, you would need to use all of the concepts we've previously learned. But here, we're dealing generally with the rod itself that's twisting. So, what we need to do is set T equal to that 30 kip inches. The radius is going to be that 2 inches, and then J is pi over 2 times 2 inches to the power of 4, which what did we get for that? $25.13, yes. And what are the units of this? Inches, just inches? Not inches squared. I heard somebody say it. I don't know who. Oh, you did? Thanks for being honest. Inches to the 4th. It's just like IX and IY. All right, so the shear stress just gets plugged in 30 kip inches times 2 inches divided by 25.13 inches to the 4th. Our units are consistent, so no conversions are necessary. And we get that the shear stress is 2.39 KSI. So that's what this is, 2.39 KSI. C right. Yes.
And we don't keep the negative for this one, right?
It's just generally like a directionality thing. I guess a good thing to do would put the negative sign just to indicate the direction that the shear stress is occurring. So, yeah, that would be a good thing to do. All right. Now the last thing, I want to make this rod exactly 24 inches in length. What's the twist angle at the end? Can you guys calculate that for me? This is where some of you might get tripped up. Oh, I forgot to mention, you need a material. Let's assume this is, I don't know. Let's say A36 steel, just to keep it simple. Get it, Emily?
Oopsie.
What'd you get?
I don't know if it's right though.
I don't care. Say it. You got this.
So I'll say it's right.
Say it. Come on. I'm sure it's right. You want to give it a shot? What'd you get?
Okay. I use the T L over G J.
Yeah.
So plugging in the 30 kip, basically 30 kip inches, the 24 being green,
Mm-hmm.
divided by the 1.2, and 25.13. I got 1,615.5. Is that correct?
Radians? Now here's a way of understanding if that's right. Multiply that by 180 and divide it by pi. And that's what the twist would be in radians, in degrees.
But you want it in radians or degrees?
It could be expressed either or, but make sure to clearly distinct your units, because with the angle of twist, you can have two separate terms of units. You know, it's like with deflection, you can have it in terms of feet or inches. I don't care what it is in. You just have to clearly express it. Otherwise, if you say it's in feet and I interpret it as inches, it could be entirely wrong. What did you get?
So when I did that, I got 92, what was it? 92561.3318.
So it rotated 9,000 degrees.
I don't
The modulus of the rigidity.
I think your issue comes from the modulus of rigidity.
I did 11.2.
Multiplied by 10 to the 6 to convert it to PSI, or 10 to the 3 for KSI. What did you get?
I did both equations to check my answer, but in degrees I got negative 0.003.
Yeah. And it checked out to be the same, right? Yeah. So specifically, you should get roughly phi equals TL over GJ, 30 kip inches times 24 inches, divided by modulus of rigidity is 11,200 KSI. And then J we calculated previously is 25.13 inches to the fourth, which is going to equal roughly 2.56 times 10 to the negative 3 radians, which is the same as saying 0.00256 radians. Now, if you wanted this in terms of degrees, multiply it by 180, divide it by pi, and that gives us approximately 0.147 degrees. So it's a very small twist. Again, these deformations should be very small. We are dealing with linear elasticity and elastic region, which makes the assumption of small deformations. It's something we've been dealing with all semester. So you shouldn't be getting 9,000 degree rotations. All right. Now, does anyone want to take a guess at how the stress varies in the cross section? So I'll make the cross section really large. Is the stress going to be constant throughout the cross section? Is it going to increase linearly with respect to its radius? Is it going to decrease? Is it going to be maximum at the center, 0 at the edges? How do you guys think it's going to look? Emily, thanks for raising your hand. What do you think? You think the stress?
Say the question again?
Do you think the shear stress is going to be maximum at the edge, at the center, or do you think it's going to be constant throughout its radius?
Constant?
What do you think?
It'll be max towards the end.
All right. Who thinks constant? Who thinks? Well, you just raised your hand. Who thinks max at the exterior? 1, 2. Who thinks 3? Who thinks max at the center? 1, 2. All right. So, one thing I want to elaborate, tau is equal to TR over J. R is not explicitly the maximum radius. R is a position function. So it's a stress in terms of the radial position with respect to its location from the neutral axis. So, where would R equals 0 be? At the center. So, if tau at R equals 0, then what's the shear stress going to be? Yeah, it's going to be 0. So, that should give us a hint that when we're looking at it from a radial perspective, the stresses increase linearly. With tau max being located there. Does that make sense? So R is technically the point of interest. And then tau max occurs when the radius is just the maximum. So in this case here, the maximum shear stress here was towards like the outside face here. But if we wanted to find the shear stress at like a halfway point, well, we just take R equals 1 inch, which conveniently means that our shear stress is just going to be like 1.2-ish, I'd say, because then it's the shear stress is just half, because then the radius is half. So it's all linear, fortunately. Does that make sense to everyone? Awesome. Now what I want to do is another example now, since we are now familiar with how stresses work, and now we can kind of kick things up into high gear a bit. Let's say now I had a rod look just like this, and it was hollowed out on the inside. Whoops. All right. This has an outside diameter of around 2 inches and an inside diameter of 1 inch. And let's say it's fixed at this end here, and there is a counterclockwise torque of, let's say, 10 kip feet. And it has a length of around 8 inches. What I want now is, firstly, for you guys to find J. 2, for you guys to find the maximum shear stress. Or better yet, instead of saying find, I'm gonna say draw tau from the radius. So in other words, I want you guys to draw a similar diagram as shown up here. And then 3, find phi at the end. I'll give you guys a few minutes to do this. The material for this, I will say, is what's this good material? I don't like any of these. You know what? Make it 1 kip feet, actually. So reduce it by 10. And then I want this to be aluminum alloy. Specifically 7075 T6. All right. Give you guys a few minutes to solve that. Yes. It's a, the way it looks is, if you were to cut a cross section through it, all of this is material, which means it's hollowed out. So, you can't just say J is just for the inside part. Let me ask you this. What is the entire cross-sectional area? Outside minus inside, right? It's the same cross. That's really cool.
Thank you.
You got Jay? What'd you do?
I first I found the J both ways, and I just subtracted.
Nice.
And
Cool. That's good.
So I used to wait in the vertical function. Is it what it
You're supposed to use both. So the thing is, think of it like if you were trying to calculate an area, you know, you would subtract the outside minus the inside, right? It's a very similar principle.
Oh, so it's 2 minus 1. And which,
Yeah. Well, you need to calculate the j for the outside and then subtract the j as if it was just the inside only.
okay.
So don't just be like 2 minus 1 is 1 and then it's that. No. That's also wrong. Yes.
I have a question.
Okay. What's your question?
Would R just be O inches?
Would R be what?
8 inches?
8 inches as for R?
No,
What is R?
perpendicular distance.
Perpendicular distance if you're calculating torque or its position. So I should maybe reword this slightly. So here's where things kind of are confusing now. So I am going to say, for all of your notes, change this R and just add a little perpendicular symbol. R perpendicular. All right? Because this R and that R, technically two separate things, but depending on the problem can be the same value. The previous problem was a perfect example of that. R perpendicular and R were different values. So to answer your question, no, R is not 8 inches. That would be L. Yeah, so let me come up here and just change this to then be that. All right. Did everyone get it? Everyone figured out everything? Yeah? Awesome. All right. How did we calculate J? J is equal to pi over 2 times the outside radius to the fourth minus the inside radius to the fourth, right? What did we get for that? What we should have gotten, pi over 2 times outside radius is going to be 2 inches to the power of 4 minus 1 inch to the power of 4, which means our J we should get equal to 23.562 inches to the fourth. From there, I asked you guys to draw how the shear stress looks, but before I do that, I want to just jump straight to problem 3.
Did you use the diameter for that question or radius? Like for to find J?
Good point. It should be 1 minus 0.5. I messed that up. That's a few points off. So that would be 1.473 inches to the fourth. That's the correct answer. Big difference, so thank you for that.
So what?
R out is equal to 1 inch. R in is equal to half an inch. And it comes from that. You're using the radius, not the outside diameter, and it's inside diameter. All right. For phi, you could just use TL over GJ. The torque was 1 kip feet, so that's the equivalent of 12 kip inches. Length is 8 inches. Shear modulus of the aluminum alloy was 4,000 KSI. And then J, we calculated at 1.473 inches to the fourth. And then just so I get it in terms of degrees, I'm just going to multiply that whole thing by 180 over pi. And I get an angle of twist of around 0.934 degrees. Now, for tau, we could calculate the maximum stress. Tau max, let me change all of this just to be red, just so that way you guys have it as an answer. And then similarly with that, tau max, how did we calculate tau max? TR over J, right? So, for this case, we have 1 kip feet or 12 kip inches. The radius, what's the radius going to be?
Is it gonna be 1 inch?
Yes. And then J is 1.473 inches to the fourth. So 12 times 1 divided by 1.473 gives us a shear strength of around 8.15 KSI. Now, I asked you guys to draw what the shear stress looks like. Let me actually come around. Who drew the shear stress profile? Did anyone even bother doing that? I want to see if anyone. Nobody took it down?
I'm still stuck on the
The first one? Jay?
yes.
What do you think?
I got 0.59. Appreciate it.
I didn't look into like I did a mistake and then you said,
Here.
I was too long, I thought I got it right.
You did that right. You just have to multiply by
Oh, so I'm gonna ask for this.
1 to the fourth minus 6 to the fourth. And then you just multiply the whole thing by
Where did you get the 12 from?
1 kip foot converted to kip inches.
Mm.
How many feet are in? How many inches are in a foot?
Okay.
Mm. Okay.
It's a easy conversion. I could just write 1 kip foot multiplied by 12 inches per foot. I just skipped that step.
What if you didn't though? What if you didn't convert it?
Then you would get a angle of twist in terms of degree inches per foot. Do you want that?
No.
No.
I don't think so.
Or no, it would be, I think, degree feet per inches? Yeah, something weird. All right? So, nobody tried out to calculate to draw how the stresses vary. No? Lazy. I'm kidding. All right. So, what is the shear stress at the center? 0. Shear stress at the outer fibers is what? 8.15 KSI. We just calculated that, right? Now, if we are drawing this out, we will also have a tau min. So if I asked you guys, what is the max? Yes.
Where did you get 12 for before?
Okay, I'm about to just do this. I'm giving up on explaining.
Oh.
Let me do that up here as well. Now you know how it feels when I'm grading your homeworks. All right. We also have a minimum shear stress. In the previous problem, what was the minimum shear stress? It was 0, right? Because there's material all the way through. But now, there's literally no material here, which means there's no stress being felt at all there, which means that we also have a minimum shear stress. It's not 1, but you would basically calculate it using the 12 kip inches times the 0.5 inch radius divided by that J, 1.473, which because of the geometry, you'll just find is 4.07 KSI. So this entire region, there's no stress because no material. Does that make sense? Stress can only develop wherever there's actual material itself. All good? All right, I'm gonna give you guys 5 minutes. Let's come back at 7:30. Yes.
Scroll out a little bit.
Here's a fun problem. Ooh. Let me not forget. Got to make more complicated problem. This is why your entire exam is now going to be torsion only. Because I can just throw a million different kinds of problems on there. You guys are going to hate torsion at the end of the semester. More than anything else. You might like it. I don't know.
I have a feeling I'll hate it.
You have a feeling you'll hate it?
Yeah.
How do you feel about it right now?
I mean, I kind of hate it.
You kind of hate it?
Yeah.
Why?
I mean, I didn't really like any of the subjects in this class, so.
That's so bad. No. Why? Why not?
I definitely like Revit and drafting a lot more.
Did you submit your application, by the way?
I did, yeah.
Okay.
Thank you.
Yep. Did everyone make their schedules already for next semester? Yeah? What classes is everyone taking?
Taking residential, structural drafting,
Mm-hmm.
3D drawing, which is like an art class.
Okay.
It's maybe like architects. So.
Mm-hmm.
Can't think. I'm taking 2 more. Hold up.
Are you doing green building or?
No, I'm doing architectural history. I didn't want to do green building.
Do you know who's teaching structural drafting?
Professor Newman.
Professor Neiman is?
And then Leslie Kelly's teaching the other one.
Hmm.
And then I'm doing professional practice.
Mhm. I remember Professor Neiman initially emailed me. I can't remember if it was this semester or last semester, but she asked me if I would be interested in doing it. I told her yeah, but like I mean, then Professor Simon, I was just talking with him today because we're still trying to figure out who's teaching what and so on and so forth. He's like, Miles, you would probably kill him with like all the structural detailing stuff. He was like, those kids do not want to know how to properly detail stuff in terms of like a structural engineer level. He's like, just give them CAD stuff and just let them draw. He's like, don't be marking up like, oh, is it with or without the bolt holes being considered in the design or anything like that.
I'm taking that one too, but I think we're doing different days. I don't remember
I'm
which
doing
day I'm doing.
Wednesday.
I can't remember. I think I'm doing Tuesday.
I can't. That art class is the only one that's at this campus.
What's the class called?
3D drawing.
It's not in the COT program, right?
It's an art class for the elective.
I remember my first semester when I was here, I had no idea what I was doing in terms of like, you know, like making my schedule. And the guidance counselor literally gave me classes all the way over on like the East Campus within like an hour difference of like me having a class here. And so when the first day arrived, I was like, hold on a minute. What? It's not in the Riverhead building? And then I looked and I was like, shit, that says Riverhead campus. Crap.
That's far.
Yeah, I felt like reporting it to friggin' the guidance counselor's office or whoever.
Did you do it or not? Did you switch
No,
out?
there was no way. At the time I was driving this truck that was like nearing 30 years old, and like the thing like it was like months away from like dying. It ended up dying like on my way to work one day that same semester.
Yeah, my car would never.
Yeah.
Barely makes it here.
No, the thing had 180,000 miles on it already, so I was like, yeah, this thing's coming to an end. I was like, it was good to learn how to drive in, but no.
I did one class in the Michael J. Grant campus my first semester.
Grand Campus is closer to where I live. It's just unfortunate because like this program is not there.
Yeah.
I wish it was, because it would cut down my commute by about half an hour.
I'm glad because I live in Sable, so it's only 15 minutes
Mhm.
away from here.
Yeah.
I heard it's nice though.
Mm-hmm.
It's cool. I did a gym class there,
I did too.
but I like this campus a lot better.
Yeah.
That one is just kind of
I will say their library is a lot nicer.
really. I didn't go in the library, only went in the one room, so.
Their library is much more modern, I think. Right?
I saw photos of it.
Mm-hmm.
Where's the library there? Is it in the main? It's just the one building, right?
No, they have a dedicated library building, I believe.
Oh, okay. Because I think I just went in the main building,
Mm-hmm.
but you can't really walk around there.
Yeah, you can.
Oh, I only walked from the parking lot to the main building. That's it.
I think anybody can really come to the campus and just walk around. As long as it's not during, like, if it's during the academic semester, I think you need a pass, you know, like a student pass or faculty pass, I mean. But, like, on weekends, I don't think they're going to tow your car, I don't think.
Oh, I just meant like this one is very walking friendly. There's landscaping and stuff, but over there it looks kind of
Barren?
yeah.
Yeah.
Barren, that's a word.
Mm-hmm. I agree with you there.
Yeah. so
Very
I didn't even
open.
want to explore. I just went in and out.
They held a carnival there one time, I remember. I don't know, do they do that every year? Do you know? I don't know.
They do that
I never.
Every year?
I
They
just
have
know it's where we
chickens.
I just know it's where we graduated. That's all.
Oh, I didn't go to the carnival there, but they have something here, and they have chickens and goats or something.
Yeah, I've been to that.
That's cool.
All right, let's give this problem a try. You guys should be able to do it. It's just reworking the equations and just, you know, learning how to use the equations for different purposes. This time, you're dealing with the factor safety of 2. And then I also want to note, no class on Thursday, but I will be uploading some lectures that I recorded last semester. Those ones are a little bit more fast-paced, but we're going to be doing more torsion as the semester goes on, of course. So I would say not everything in those recordings is necessarily applicable as of right now, you know? So I would say if you're a little confused about some of the stuff in there, don't stress out too much about it, because, again, I'm making the entire final exam torsion explicit, and those 2 recordings, I kind of covered everything all in like 1 lecture, 2 lectures.
So this Thursday, right?
This Thursday, yeah. So please don't come here.
Do we have homework due?
Not Thursday, but following Thursday.
Oh, the following Thursday. Oh,
Yeah.
okay.
Yeah, I uploaded the homeworks. It's basically all of like the design stuff and such. And then I'm thinking of removing. When is the last day of classes? Does anyone know that number?
Like
The
final
18th.
day? I think
Yeah.
It's like the 18th.
It's Thursday.
The 18th? All right. So one of the things I'm thinking is, because like I think I'd set it up to where the homeworks were initially going to be like, there was 11 homeworks, you know, but because of Thanksgiving, or no, not Thanksgiving, but it was some other day, I forget what it was, but the class ended up getting canceled and I didn't realize it.
Veterans Day?
Yeah, so because of that, I don't think, like, I ended up posting one of the homeworks or things got kind of messed up and I didn't want to upload the whole thing. So because of that, I think there's going to be one less homework this semester, but lowest one is still going to get dropped. So, yeah. So the next two homeworks are just torsion explicitly. I think this one that's going to be due next Thursday is going to be just on the stuff we're doing today, and technically you can rewatch a lot of the videos on a lot of the stuff on Thursday. And then next week we're going to be doing like statically indeterminate members and composites. Statically indeterminate's not going to be on your exam, just like on the first exam. I'm just going to be showing you guys just so you understand the concept of compatibility with it. But yeah, all just kind of the same format.
So there's only 2 more words left?
Yeah.
Oh.
Yep. Yeah. Pause this. Oh, I just realized you can't use annealed copper. I don't give you an allowable shear stress.
Yeah, this is
Do not use annealed copper. Use. Oof. Gray cast iron. There we go. And again, I'm losing my mind. I just chose another material that doesn't have a shear strength listed on the appendix. All right, somebody pick a material that has a shear stress on the appendix.
cold rolled.
Annealed stainless.
Yes.
Annealed stainless steel. There we go. Third time's the charm. Does it say annealed stainless over there? Okay.
have a question.
Yes.
Do you have to like go arm in situation to like solve this?
Yeah. Where's the maximum stress occur?
0?
Nope. Already wrong. Look at the diagrams we've been drawing. Where does the maximum shear stress always occur? I already have an answer. Yeah. Emily, what did you get?
I'm not gonna lie, my paper's blank.
Your paper's blank. Okay. All right. Well, I have an answer. I want to walk around, see what everyone else has. Yes.
So, I understand paper also is here. We say it's
It is.
right in the middle.
I don't know what T-Max is.
This one, I wrote T-Max equals
I know what
Yeah,
the shear
we're
is.
designing
I
the
know
rock.
what T is.
So, are we using the 2 for R?
Nope. That's the factor safety.
So, we can find T-max in these equations without R or length.
What's the limit of the material?
G.
That's the shear modulus. What is it? You got to work backwards on this problem. What is the maximum shear stress that the material can handle?
22
22 KSI. So what is your tau max?
22
22 KSI. What's our torque?
200 kips.
Kip inches, right? There's a factor of safety of 2. What does that mean?
Multiplied by 2.
So what's our torque that we're using for design?
400.
400 kip inches. Next thing we need. What is the radius? We don't know that. Where does the maximum shear stress occur though? At the maximum radius, right? Which is just going to be R. So we can just replace it with R. And then what's the last thing? Polar moment of inertia, right? What is that in terms of? Radius. So from there, we basically want to back calculate what the required radius is, and then to find the diameter, just multiply radius by 2. Does that make sense? You guys want to work on it together?
Yeah, let's see how.
Okay. All right. Let me erase my solution, just so that way I can do everything with you guys. Do 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 do. Man, I was hoping you guys would be able to do everything backwards. Guess not. Not yet, anyways. I'm so disappointed in everyone. All right. Maximum shear stress occurs at the outer radius, R max. But R is basically what we're trying to find, right? Which is just equal to the diameter divided by 2. So we know that. What is J? J for this is just going to be pi over 2 R to the 4th, right? So from there, we also have T, which T is just going to be 200 kip inches, which you multiply it by the factor of safety, which means 400 kip inches is going to be used in design. And then lastly, tau max is equal to 22 KSI, which is from your appendix. All right, from there, what do you guys think we should do? What equation do you guys want to work off of? I would say use tau is equal to TR over J, because that has everything that we need, right? It has the shear stress, it has the torque. Radius we don't know, and the polar moment of inertia we don't know, but we can figure those out because they're all functions of the radius. The real trick with these design problems, particularly for torsion, the hardest thing is the algebra. All right, so pay close attention. We want to replace all of the terms. So the torque, or the torsional stress, shear stress, is just going to be 22 KSI. The torque is going to be 400 kip inches. The radius we don't know. And then the polar moment of inertia we know is pi over 2 r to the fourth. We can simplify this slightly because this r is going to cancel. So that becomes r cubed, right? You guys agree with me with that? That's just basic division. We can rewrite this expression to then say pi over 2 r cubed is equal to 400 kip inches divided by 22 KSI. R cubed is just going to equal 2 over pi times that 400 divided by 22. How do we get rid of the cube? Have you square root? It's close.
Yeah.
You have to take a cube root. So you have to take a cube root of both sides. So r is going to equal the cube root of 2 over pi times 400 divided by 22. Which gives us a radius of 2.26 inches. Everyone knows how to do a cube root on their calculator, right? You don't. I knew that was going to be an issue with some of you. Let me see your calculator really quick.
I was gonna watch YouTube video, but you don't really do it.
That's square root.
Yeah.
There we go. Press math button
Oh.
4.
Okay, thank you.
Yep. Everyone get it? All right. So, what does the diameter have to be then? Diameter is 2 times the radius.
4.52.
Yeah. All right. Now, for rounding to the nearest 16th of an inch, what would the diameter be that we would use? Near 16th of an inch.
Use a 5/16.
Why? Why not 4.5?
But you always round up.
Yes. So, use 4 and 9/16 of an inch because we have to maintain a minimum factor of safety of 2. In something this close, an engineer may just say screw it and just use 4.5 inches. You know, like, I mean, then the engineer's, taking a risk, but if they have experience and they're like, it's fine, they can sign off on it, but that's their risk, But 4 and 9/16 would be the appropriate thing to do. All good? Awesome. Now, what I want you guys to do is a get out of jail. I know you haven't seen one of these in a little bit. Thought I forgot about them. So, let's see. Let's make the rod there. Let's say we've got an applied torque here of around 2 kip feet. And then we're going to actually make this a stepped shaft. The dimensions are as follows: 4 inches, 4 inches. This one has a straight outside diameter of around 3 inches, and this one has an outside diameter also of 3 inches with an inside diameter of 2 inches. And all I want is, if this is gray cast iron, I want you guys to find tau max, so the maximum shear stress in the entire rod, and also the max angle of twist. Actually, I'm not going to word it like that. I'm going to say this is going to be A, B, and C. I want you guys to find phi AB, phi BC, and then the rotation at C. This should be doable. All right, this should be doable in about 15 minutes, I think. Not asking you guys to draw the profile, just repeat the math.
I saw those.
I hate wood design. Aggravates me. And I will have a set of solutions up here for you guys to take pictures of at exactly 8:15. Because I'm sure some of you want to just leave afterwards and not stay late. All right, everyone's done? Kidding. Get out of jail, 12/2/2025. Let me reword this to be Who here didn't get a flash drive, flash card, by the way? Everyone's got one? You didn't, right? And you didn't either, right, Christian? Question? Remember how we did it for axial compression and tension? How we found the change in position?
Yeah, I don't know how to do rotation.
How do we do that? It's the same exact thing. Mike, you got it?
I'm trying to find out how to find the rotation.
Trying to find a rotation?
Yeah.
Let me ask this. What do you get for the max shear stress? It's not that good.
Okay, well, I don't know if that's right.
How did we calculate it?
I saw
Those numbers seem, because remember, you're dealing with radians. Well, yeah, the units are incorrect, so you would lose points on an exam. Be careful with that, but you would use the radian version in the radians here.
So
which-
basically just what
yeah. This one looks right. Yeah, that one would be right, I guess, too. I think you're just rounding it. There's just a significant amount of round off error because you're using these numbers.
I'll change.
So, well, they are in radians, I think. I just think you forgetting to multiply it by that 180 over pi conversion.
Yeah, I think that's.
So the max shear stress I think is right, but yeah, I would say for the total rotation at C, look back at at the beginning of the semester notes. How did we find the change in position due to elongation or compression? What would we need to do? Yeah, but there's a particular thing that we did at the beginning of the semester. If you have one bar that's elongating and then another bar that's elongating, what do you do? What?
Cut sections and find, like compatibility.
Not quite. It's like if you have one rubber band and it's wrapped around another rubber band and then you stretch it, what's the total elongation? It's going to be stretching both rubber bands, so what's the change in position going to be? Want to know?
Is this what you got? Like,
Yeah.
okay.
Where are you at?
I don't know. Well, we'll start with this.
Okay. 2 times 4. Keep in mind unit conversion. You're doing radian feet per inch right now. So be careful with how you present your units. All right? That's your first thing. Figure it out. How about you, Christian? What'd you get? You got the majority, right? Right, radians, stress. Oh, that's the J. Yes, J is right. Shear stress. Generally, you would want to check this one as well, but I assume you would already send it shear stress. Was good. How would you find rotation at C? Maybe later on in the semester, maybe just slightly, maybe a little bit more. Here's an example. Just want to make sure everyone's got the majority of it. Still working it. How about you?
Are you supposed to listen to
Mm-hmm.
okay, so
Yeah. Because now it's like a step thing, so you need to check both sections. Give up? No?
I'm a computer.
Okay,
PC, like, for real time.
figured out yet? Let's see where you are.
So, I switch to
Inches times 4 feet divided by 4,100. Keep in mind,
Yeah.
24 is in kips, you're using 4.1 times 10 to the 6, which is PSI. So now you're using radian kip per pound. Consistency in units is key. Units. I think that's where I take the most points off throughout the entire semester, is units.